static equilibrium we are going to apply for extended objects, meaning not particles, at rest. If you had no net force and no net torque, technically maybe it could be moving but in a constant manner, but we're just going to use it for objects at rest. Nice simplification. Now, it is important that both of these are true. If you have no net torque, but you do have a net force, that could be translational motion. If you have no net force, but you do have a net torque, then you can have rotational motion with angular acceleration. So one of the things that's really nice to use here is that you can pick any pivot point you want. And the idea being that it's not actively rotating. Net torque is 0, not rotating, pick any pivot point you want. Now, usually there's going to be some choices that are more convenient for the math, but we'll look at what some of those are. Now, the limitation is that if the forces and torques aren't balanced, if there actually is a net force or net torque, then this model doesn't apply. So this is extending our previous equilibrium model to include torque as well. I want to talk here a little bit about representations, and specifically what is everything that you're going to want to label when you're doing static equilibrium problems. And I'm going to go through 2 examples. So in this first one, you have a person standing over here on the left, and then you have a person who is walking to the right. Notice that this beam is on 2 little ladders, but it's not nailed down. So it's possible for it to stay on this ladder and start to lift up this one. Now you're given distances, and in the problem you would be told the masses of each of these people. So the question is, how far can this person make it to the right? Can this person make it all the way to the right without it tipping? Or if not, how far could they make it? So this isn't a sufficient representation. It's a start, it shows a few helpful lengths, but we really need to define a lot more. So the first thing we want to do is simplify the scenario a little bit. So in this case, we have 2 pivot points, and I'm showing them with these little triangles. However, the second thing you need to do is figure out where your center of mass is. And in this case, it's the center of mass for the just the beam, the big thing of wood itself. And that's right here. The next thing that you want to do is define your coordinate system. And I'm probably going to define this point here as x equals 0. And then this is my positive x hat direction. Now you can choose whatever pivot point you want, and in general you want to have x equals 0 be your pivot point. So even though this is my center of mass, that isn't necessarily going to be a pivot point. Oh, never mind. I was saying let's have this be the pivot point, the book was saying have this one. Either one would work actually. So the book wants you to use this as your pivot point. Now, if you're going to do that, you actually probably want to change your coordinate system. And instead of having x equals 0 there, use x equals 0 here. Have it be at your pivot point. So we then have some known masses of our people, and we then want to label our forces and where they are. Now this is labeled as a normal force because person A is standing here and pushing down. So this is the push from the person onto the bar, the beam, whatever it is, and then there's some distance that our second person is standing at and is pushing down there. Now this is going to remain a variable because it's what we're solving for. This dm distance here is the center of mass of the bar, and since the entire bar was, and you would figure that out from subtraction based on knowing the entire length of the bar and the different distances. So here it's listed as 2.5 meters, but you've actually had to do some work to get there. Then you have 2 normal forces here from where this is pushing up. Now you don't actually know a priori what these are. So this is something to be careful about, that it isn't necessarily true that the normal force here equals this person's weight and the normal force here equals that person's weight. What about the weight of the bar itself? So you would have a lot of math to do after this, but you would want to at least start by drawing this extended free body diagram, showing all of the forces, showing your coordinate system, starting to do out some calculations. And then the other thing that you would keep in mind here is that you're using the equilibrium model. What that means is your net torque is equal to 0 and your net forces are equal to 0. I want to show you another example, which is a very classic physics problem, which is a ladder that is tilted against the wall and actually has friction. It could have friction on one or both surfaces. And the statement is, what, for instance, angle or what distance from the wall can it be without it slipping? Or in this case, all of your distances are defined, and the question is, what is the coefficient of friction that prevents it from slipping? So we need to show the size and shape of the object. This is obviously a side view, and we're approximating it as just being a very simple object. So even though ladders are slightly more complicated, you do want to simplify down the shape. You then need to have where your center of mass and your pivot point is. In this case, your center of mass is center along the length, but you would maybe want to figure out where it is in terms of x and y for later work. The pivot point could be at the center of mass or not. In this case, we're going to use the pivot point down here. Now again, in general, you might be told sometimes where the axis of rotation is, but for a static equilibrium problem like this, you can choose whatever pivot point you want. It's helpful to use this point since two forces act there, so we know that neither of them actually exert a torque. Make sure that you have your coordinate system, which this figure from the book doesn't have, but we would want to definitely have some sort of x and y so that we can actually talk about forces later in terms of pointing in x direction and y direction. Now, because it's really helpful to have the pivot point be our coordinate origin, we can actually define this to be x equals 0 and this to be y equals 0. So all of our distances in x are going to be negative, but that's okay. Lastly, if we know our net force and our net torque, let's specify those. Since this is a static equilibrium problem, we do know these. Oops. And make sure that, as always, you're writing those off to the side rather than just trying to label them on the diagram itself. So then what you would start doing is looking at each of these and adding up the x components of force and saying that they must sum to 0, the y components of force and saying they must sum to 0, the torque, which you don't have a torque from either of these forces because they act directly at the pivot point, but you do have a torque from each of these, and you would have to take into account the angle. And again, one option would be that you use the entire force, but you only use the distance that is perpendicular. So when you do this, though, something that's really helpful to keep in mind is that we don't necessarily know a priori like what these normal forces are. This kind of depends on what the question is. Make sure that you keep these general initially, and you can use FNet to then solve for them and then plug that into your torque. Depending on what the problem is, and I have a version of this that's a little more complicated, if you just assume that you know what the normal forces are, you're really likely to be incorrect and have problems.